I'm going to be talking about work that I've been involved in for quite a few years, since my PhD. And I'm going to be talking, as you can gather, about a set of elements that you don't normally come across. These are the noble gases. So as a geochemist, it's a strange set of elements to choose because they're completely inert. They don't do any geochemistry. But I'm hoping through this lecture I will describe to you exactly how we can use them, why we can use them, and why they're so important for understanding crustal fluid flow in the ground. So noble gases, they're not just used for looking at crustal fluids. They're a set of traces that have got some very exciting applications across the sciences, across the natural sciences. And for example, noble gases dissolve in water as a function of water temperature. So if you measure noble gases in water, you can tell the temperature that the water was at before it went into the ground to within plus or minus 0.3 of a degree centigrade. So you can measure the concentration of noble gases in water, and instantly you have a climate change record in the ground beneath your feet. Mantle and atmosphere evolution. The noble gases have come from a variety of different places from around the solar system. And the different processes that formed our planet are preserved in the isotopic composition of the noble gases, in volcanic gases, in rocks that are brought up from the mantle. So a huge range of types of application. Stellar processes. When a star explodes, tiny diamonds are formed, microcarbon species are formed, graphite. They trap noble gases which tell us about the last stages of a star's life. The information in noble gases is absolutely phenomenal and fascinating. And of course, anybody in earth sciences realizes that understanding time is absolutely fundamental and critical to the whole understanding of the earth sciences. Some of the noble gases are produced by radioactivity, and for example, potassium decays to argon-40, and you can get dates in minerals and reconstruct the entire Earth history from potassium-argon dating. And some of the very first radiogenic date ever used was uranium decaying to helium-3 in uraninite. So these are tried and tested tools, fundamental to a whole range of applications in the earth sciences. But today I'm going to be talking about crustal fluids and how we can apply them to understanding fluid flow in the ground. This diagram is designed to scare you. This is why we can use the noble gases. We have in stable isotopes, traditional isotopes, oxygen isotopes, 2 isotopes we use, carbon isotopes, 2, 1 radioactive, 3 isotopes, hydrogen isotopes, 2. Within the noble gases, we have 23 isotopes. So what I want to convey to you is the richness of information if we can unlock the secrets of the isotopic compositions, the fingerprints, the history that is preserved in this geochemical spectrum that is available to us. A geochemical spectrum that is not compromised by chemistry. So we can see through the chemical processes because these guys are completely chemically unreactive. So when we see changes in these compositions, we're seeing changes in the physical chemistry, in the physical processes, not the chemistry. But it's simple. This is an intimidating diagram, but it simplifies into 2 components. We have gases that were brought to Earth when the Earth formed, and we quite often call these primitive isotopes. They come to Earth with a specific isotopic composition, and added to those, we have isotopes added to them through radioactivity. What we need is an environment in which the primitive isotopes are in low abundance, which means that the isotopes produced by radioactivity significantly change the composition, the spectral fingerprint that allows us to analyze these and distinguish these different components. And that's just what Earth has done for us. Over time, when I say over time, in the first 50 million years of Earth's formation, the Earth lost almost all of its volatiles. Although we look around us, we see water, we see air, is a tiny, tiny, tiny fraction of the volatiles that were available when the Earth formed. And that's what allows us to use the noble gases in terrestrial studies. The relative amount of the noble gases in the systems around us is really, really small. And that means that the residual atmosphere, after it's been stripped and wrenched and torn off the planet, the residue that we see around us today has got its own very distinct isotopic composition. The continental crust contains about 50% of the radioelements in the entire planet. It's the way the Earth has worked and concentrated uranium and thorium and potassium into the continental crust. So the continental crust contains absolutely no noble gases and is sitting there generating these radiogenic gases. And then deeper within the Earth system, within the Earth's mantle, down to 2,900 kilometers, right down to the core mantle boundary, we have the very remnants of the isotopic compositions preserved from the accretionary process. So we have 3 reservoirs that have differentially evolved. Each has got a very distinctive isotopic composition. And that is exactly what we can use when we look at crustal fluid flow. We've got 23 isotopes. We don't always use them all, but we have that capability. And it simplifies into 3 sources. The atmospheric reservoir dissolves into groundwater, and I've already said how well we understand the way in which air dissolves into groundwater. That's the concentration of noble gases, and 20 neon and argon-36 pretty much only come from air. So these are traces of not air, but groundwater contact in the subsurface. All of the time within the crust, we're building up helium-4, neon-21, argon-40, and a range of these radiogenic isotopes, adding to the systems, which means we've got temporal information, time information about the fluid systems we're looking at. And because each of these systems, the atmosphere, the mantle, helium-3 is a mantle, only come from the mantle, we can, in any crustal fluid, measure the isotopic composition. And from the isotopic composition, I can tell you exactly how much has come from groundwater, how much has been from radioactive decay, how much has been from magmatic volcanic gases. And that doesn't matter whether you're looking at an oil field, a gas field, or a single fluid inclusion. The sensitivity of the analysis that we've got allow us to measure down to not quite atom level, but if our samples contain more than 10,000 atoms, then we can start getting useful information from these systems. Importantly, once we've identified the groundwater contact or the radiogenic buildup in our target fluid, we know the elemental ratio. We know the elemental ratio of helium to neon to argon to krypton to xenon in groundwater. Where that elemental ratio changes, that is because we're looking at the physical processes of fluid movement. If we see change, that is consistent with diffusion, we can identify and quantify diffusional processes. If we are looking at changes which are due to multi-phase interaction, they will relate to the different solubilities of the gases. So immediately, we've got information about not just where the fluids come from, but the physical processes that have brought them, and the extent, the magnitude, the quantification of those physical processes. So that is the background to why we can use the noble gases. And what I want to do is show you a couple of data sets showing you how we've applied those to identify these processes and the quantities in the systems we're looking at. So I'm going to start with a really simple data set. This is quite an old one now. This is some of the earliest work that I did. And we are looking at the Pannonian Basin. And this is a cross-section across the basin. This is a Miocene rifting basin. So this formed about 15 to 20 million years ago. It rifted apart, filled up with sediments, and at the top of those sediments there are now gas and oil traps. And these black dots are mainly gas fields. And I'm looking at one of these gas fields, the Haituzapozlu gas field. This is a cross-section through the gas field, producing gas down to 1,200 meters depth, multiple production levels. And this is the first noble gas data that we really developed for identifying measuring noble gases to see what they could tell us in gas fields. Is that most importantly, we see a very well-behaved, clear behavior in the neon isotopes, in the argon isotopes. Within the helium isotopes, there's a bit more scatter. The most important thing that we have to resolve is the difference between air dissolved in groundwater from air which contaminates our samples. Are the collection techniques working? Are the sample transport techniques working? Are our measurement techniques working? And when we see well-behaved data like this, the answer to all of those questions is yes, it is. We've got a good strategy for getting clean samples, which gives us now the ability to resolve dissolved groundwater and dissolved groundwater containing more radioelements like radio-derived 21 neon and argon-40. So, stepping back a little bit, now we know that all of this is coming from the groundwater. Argon-36 is our groundwater proxy. If we have argon-36 in our gas field, it can only come from the groundwater. If we know the concentration of argon-36 in our gas field, then we know the amount of water that must have interacted with that gas field. The minimum amount, if that water completely loses its argon-36 and strips into the gas field, the minimum amount, just by doing a simple mass balance, how much water is needed to supply the argon-36, for the one gas field we're looking at, requires 1,000 water that would fill 1,000 cubic kilometers of the local basement. One gas field. You saw that earlier picture where there are multiple gas fields. In this particular environment, groundwater is playing a fundamental role in the transport of the gas from where it's generated to the trapping structure. And we can investigate that in even more detail. Maybe. Here we go. When methane dissolves in water, you can put more and more methane into that water until it reaches saturation. When you reach saturation, you will develop a gas phase. The water itself has a constant argon-36 concentration, and when you develop that saturation limit by pumping it full of methane, the first gas that forms will have a characteristic methane to argon-36 ratio. And so as a function of depth in the basin, we can predict what a gas exsolving from solution would look like. And we can plot our data on that diagram. So this is the methane argon-36 ratio. We've calculated for us a very simple model. And our data is completely consistent with the gas in that gas field being exsolved from the groundwater system. We're looking at a regional flow of groundwater reaching a point of saturation and then degassing to form this entire structure. We're understanding the mechanism of transport, which is quite different to many other systems. This is data from the Vienna Basin, where the methane to argon-36 is well in excess of this solubility model. And this is gas that has migrated as a free buoyant phase. If you're in an environment where you want to understand the principal control of gas migration, whether that's controlled by the hydrogeology or by buoyancy, you've got two fundamentally different processes to consider. This technique allows you to distinguish between those. And closer to home, this is another study. This is from the Dosso degli Angeli gas field in the Po Basin. Much deeper system, but again, quite clearly very closely related to a degassing process. I'm going to move a little bit away from hydrocarbons, but I hope in the next few slides you'll see where hydrocarbons play a role. Our society also, beyond hydrocarbons, needs helium. It's not a major gas, but without helium, we wouldn't have half of the microprocessors we have. It's fundamental in the semiconductor industry. If you have ever had an MRI scan, or have employed high-tech, high-energy beamlines for advanced. All of these require liquid helium for cooling. Without helium, we would lose a huge amount of this technology. And recently, the supply of helium has become very insecure. The current global consumption, just for reference, is about 8 billion cubic feet per year. And because of the high-tech applications using helium, this has risen by about 130% in the last 10 years. 2012, these were the sorts of letters that, as helium users in the UK, we were receiving from the helium suppliers. The volume we are able to supply will be reduced from BOC Linde Group. Within the US Congress, discussion was brought about the shortage of helium and its impact on the semiconductor industry. So if we want to understand the supply of helium, let's go to a natural gas field where helium is one of the principal outputs. Now moving to this is a methane field, so you can see we're back to hydrocarbons. This is one of the giant gas fields in the US. It's about 300 kilometers in length. Within the gas field, you can see that one of the components, it averages about 0.8%, but some of those gases are producing with up to 1.8 to 2% helium. For commercially exploiting helium, you need approximately 0.3% to make the capital investment in the helium extraction worthwhile. So this is a wonderful case study for a helium-rich natural gas reservoir, which until the 1980s provided, I think, between 80 and 90% of the entire Western world supply of helium. It's now largely depleted, and other gas fields have taken over. One of the key things to notice is that when you find helium, you always find nitrogen. And helium is produced, this is one particular isotope of helium. This is helium-4. It's generated by uranium decay and accumulates slowly in the crust. But it's always associated with nitrogen, which is certainly not from radioactive decay. So why are these associated? So we can look at this in a little bit more detail. We can look at some of these noble gases that I've been working with. I talked about argon-36 being a groundwater proxy. Neon-20 is also a groundwater proxy. Suddenly, we can see that neon-20 is directly proportional to the helium content of the gas that we're looking at. So immediately, this is telling us that groundwater-derived gases are intimately associated with the crustal helium. And if they're associated with the helium, they're also associated with the nitrogen. And we can play a simple geochemical trick. If we have a plot like this, and we want to investigate whether it's mixing between a variety of geochemical components, if we normalize to a common element, and I'm normalizing here to nitrogen, if we form a straight line, that is because we are only mixing between two gas components. So despite this reservoir being 320 kilometers in length, only two sources of gas matter for the neon, the nitrogen, and the helium system. One of those sources of gases is pure nitrogen, nothing to do with helium at all. One of those gases is nitrogen, which is associated with helium and associated with groundwater. So how can we bring these observations together to understand how helium is accumulating in this system? We can look at the nitrogen in a little bit more detail. As soon as we know that the nitrogen is coming from two sources, we can look at the isotopic composition and resolve what those two sources of nitrogen look like isotopically. Again, we've got this fairly good correlation between the nitrogen in the helium-rich component, the nitrogen in the helium-poor component, and we can identify the isotopic composition of each, which tells us where that nitrogen is coming from. The nitrogen that's not associated with the helium is completely consistent with an over-mature hydrocarbon source. The nitrogen that is coming in with the helium at -3 per mil is much more like the type of nitrogen that you would fix in clays. Think of the deep granite basement beneath this system. weathering, reacting, generating clays. Liberate those clays with the helium, that's exactly the signature you would get. So we're now starting to see that relationship between the role of the nitrogen, different sources of nitrogen. Groundwater plays a fundamental role. And just like that first study, we can calculate the nitrogen to helium to water ratio using the neon 20 as our water proxy. And that tells us that the helium and the nitrogen, until they interact with the hydrocarbon system, are in solution. They're at a level that the pressure and temperature of the basement would dissolve completely the helium and nitrogen. And for this particular environment, you will not find a commercial reservoir of helium unless there is a pre-existing hydrocarbon component in that system. So now we're starting to develop the base for exploring for helium. Remember, helium is produced in very low concentrations in large volumes of the crust, slowly over time by radioactive decay. Time's required. Nitrogen is associated with that helium. Nitrogen and helium are dissolved in the water, and we need this degassing mechanism. So it's very simple to put together an exploration checklist in exactly the same way that we explore for hydrocarbons. Source, hydrocarbon, you look for organic matter. For the helium system, you need uranium and thorium decay. Maturation, time, primary migration, heat and pressure, secondary migration, buoyancy or driven within the groundwater system. Entrapment, we need exactly the same structural traps, and we need trap integrity over time. Release of the helium is through tectonism. Back to the very first case study I showed you, one of the other outcomes of this study was that we were able to understand the helium flux. The rifting of this basement has an order of magnitude higher helium flux coming out of that system because of the extension and heating of the deep basement which has produced the helium. We can look at Yellowstone. This is work from the USGS that was published just last year. Underneath Yellowstone, the stable continental US crust has got a plume rising up beneath that. Volcanic activity heating that crust, releasing the helium out through the Yellowstone geysers, out through the Yellowstone gassing system. You know, you can just look at that and you can feel the helium as it comes out. The helium released, the flux from there is huge, 13 billion cubic feet per million years. This is only one spot, but that is twice the global use of helium being liberated from the crust from that one spot on Earth. It doesn't have any trapping structures, so we're missing a trick there. We can go closer to home. We can look at the Idrocarburi related to the Rheingraben. This is a study by Weinlich et al. 1999, showed very nicely at one of the volcanic centers, pure magmatic volcanic gas. As you move away from the volcanic gas center, more and more of the crustal gas, again 1 to 2% helium. As you move away from the crustal centers, this is the helium 3-4 ratio, magmatic signature for the helium, crustal signature for the helium. We can use helium as a tracer to explore for helium. Makes sense, doesn't it? This is a work that is currently unpublished, but we're looking at exploring with a small startup company called Helium One, who have identified helium-rich springs related to the Tanzanian craton. This just gives you a perspective of the amount of helium down there. Huge, huge amounts. The amount of uranium and thorium distributed within the Tanzanian craton down to about 15 kilometers depth would have generated 3 times 10 to the 6 billion cubic feet. So 3 million billion cubic feet. Remembering that global use today is only 8 billion cubic feet. We don't need a very high efficiency of release and trapping to generate commercially valuable deposits. We're looking in the Rukwa Basin, where we have helium-3, helium-4 ratios. I'm plotting helium-3, helium-4. We have wonderful two-component mixing between carbon dioxide-rich systems and crustal helium-rich systems. And in principle, we can use the soil gas the helium-3, 4 in the soil gas, and we can explore from the volcanic center to find the limit to where the helium becomes commercial. And there are trapping structures in this system, and currently, and these aren't my estimates, these are independent estimates, suggest that the current trapping structures have the capacity to hold up to 56 billion cubic feet. So this one area has the potential to supply the entire global need of helium for the next 8 years in this one site. So these are the types of things that you want to look at when you're looking for helium. But remember, the key issue here is what phase is this helium in? There are no hydrocarbons in this system to degas groundwater. So the current issue is whether or not that helium is in a gas phase or whether it's dissolved in a water phase. And at the moment, that's a current component that people are very interested in. Carbon dioxide and climate. I'm going to skip through this for time. We've done some very nice work understanding how carbon dioxide is stored in the continental crust, but I think I'd rather spend a little bit more time going carefully through the next application. So I'm now moving right back to hydrocarbons. This is coal gas. So this, before shale gas really took off as unconventional methane gas source, the largest unconventional producing gas field in the world were the coal gases in the San Juan Basin. This is beds of coal that have been uplifted. So the bed of coal would have been laid down in a very nice flat layer. Tectonism has uplifted the northern section of this basin and fractured the coal. And that fracturing of the coal has allowed groundwater in, and the groundwater has promoted biodegradation. And that biodegradation has produced vast, vast amounts of methane, and that is what has been commercially produced. And one of the questions we were interested in, we've got the perfect tracer for understanding groundwater involvement. What is the role of the groundwater in that biodegradation? Is the volume of groundwater important, or is it just the trigger for starting that biodegradation? And over what time do we require that process to operate? This is just showing you some of the chemistry, typical biodegradation products, carbon dioxide and methane. And in the southern section of that basin, we have got coal that is unaffected by the biodegradation and has a much more classic thermal maturation of the coal rather than biodegradation. Looking at the helium isotopes, we're not seeing any distinction between these two systems. But what we can do is look at the processes operating on those gases. Neon-20 comes from groundwater. Argon-36 comes from groundwater. We know the ratio at which they are in the groundwater. When that first bubble forms, simple physical chemistry to calculate what the composition of that gas looks like, and it would plot up there somewhere. Equally, helium-4 and argon-40, we know the ratio at which they're produced. It would plot up here as well. All of our data fall on exactly what you would predict for a solubility-controlled open system degassing. As you bubble gases through water, you strip the gases out as a function of their solubility. The least soluble ones come out first, the heavy ones hang around a bit longer, and you generate that dotted line is the model, and you can see the data provides a very good fit to that very simple model. Within the context of that model, each one of those points tells me the amount of degassing that has occurred in that system. Well, we can use that to reconstruct what the original gas looked like, and if we understand the original gas, we can calculate, for example, the concentration of helium-4, how long it would take to build up that helium-4, the age of the process we're looking at. We can calculate with simple mass balance the amount of water involved in this process. Quantify the groundwater content. One of the interests for this site was can you pump carbon dioxide down onto coal bed methane, enhance methane production, and also trap the carbon dioxide as a CO2 repository for mitigating greenhouse gases? You certainly would not want to put the carbon dioxide into the first 5 to 10 kilometers of the basin system because it's flushing through with a large volume of water. We can measure it. We get an idea of how long it takes to generate the methane produced, and we can take this, I'll skip through this, we can take this exact same strategy, this exact same approach to other systems. This is biodegradation of shale gases. If you take shale, take it to the laboratory, biodegrade it, you get a completely different rate of production of methane than you would get from the natural environment. These are ways of ground truthing the results you get from the laboratory. We are able to date how long it takes for biodegradation of methane to form commercial reservoirs to form. And interestingly, the numbers that we were getting from the Illinois basin, recharged by glacial melting, we're looking at, on average, about 330,000 years required to generate these commercial quantities of methane. Very similar sorts of ages for the generation of the biodegradation in the coal gases in the previous study that I was showing you. So some degree of coherence, only a few studies, so I think you have to be very careful, but certainly some coherence in the length scales, time scales. And if you are looking for biodegraded products, then you now have a time constraint for water incursion into that system to think about. But what have we just done with that San Juan coal bed gas field study? We've calculated the amount of gas that has moved through the water. That is the function of establishing that Rayleigh fractionation open system degassing model. Each one of those points I showed you told me exactly how much gas had to have been lost to take me down that Rayleigh fractionation line. We have a technique for understanding and actually quantifying the amount of hydrocarbon movement through basin systems. And this is a paper we published just last month doing just that. So my postdoc, Peter Barry, has led this with a former student of mine, Mike Lawson, who currently works at Exxon. And we're looking at, this is a classic fill and spill. We chose this study because we know it's an open system. We're in the North Sea. We're looking at a cross-section through the North Sea. In the deeper parts of the North Sea, we are generating methane gas through pressure and temperature. That gas is migrating up dip, filling the structural traps in the Sleipner vest, filling and overfilling it and spilling gas to fill structures higher up the stratigraphic or higher up the basinal sequence. It's a classic fill and spill. The question we're asking is, how much has it spilled? Can we start to really reconstruct the volumes of hydrocarbons moving through these types of environments? This is the first attempt that we've had at this, and we did not have access to sampling ourselves. We took samples that were collected for stable isotopes, which aren't that appropriate for noble gases. It is easy to contaminate our samples. That was the point of the very first slide I showed you. We have some degree of contamination, but we can spot it, we can correct for it, and we can remove that and strip that out from our considerations. You know, we clearly have, looking at the neon and looking at the neon isotopes, the argon isotopes, we clearly have 3 samples in the suite that we've collected, which are swamped with air and we can't use. And I would certainly be very suspicious of any sampling technique that gives us that level of air contamination, that these samples all have some degree of air contamination. And so I'll use for reference this sample B06, which is our least air contaminated sample. I'll show you what we can do with that. If we bubble our gas through buoyant migration and fill a reservoir, and that reservoir does not spill, all we do is strip out the gas from the water and put that water signal into that gas field. And it will then just not change. The more gas we put in, just the more dilute it will come. If we fill and spill, this is identical to an open system Rayleigh fractionation process. And this diagram perhaps isn't the clearest, but rather than just using neon 20, and I've showed you how to use neon 20 and argon 36, building up the sophistication. So now we are starting to use not just the neon, not just the argon, but also the krypton and also the xenon. And we can start to look at patterns. For a classic closed system, our first bubble would have this particular pattern. This is all normalized to what we would expect to find in air. As we fill and strip that water, our pattern would shift to this value of the normalized value of 1, air saturated water, ASW. Within an open system, we would Rayleigh fractionate, and we would, as a function of solubility, migrate past that air saturated water limit. And that's exactly what we observe in our least air contaminated sample. If we look at our air contaminated samples, they look like air. No surprise. BO6 has not reached the air saturated water limit. It's gone past the air saturated water limit and is in exactly the field we would predict for open system behavior. As soon as we understand the physical constraints, we can construct a simple model which identifies within that model the quantity of methane that must pass through this system to take us from that first bubble down the open system migration Rayleigh fractionation path. And this is an expansion of that, showing that even the sample BO6, this is at the trajectory for air contamination. So you can see we're seeing through these improperly collected samples. For this particular sample, BO6, we predict exactly how much gas must have migrated through to give us this particular value. And it's approximately 8 reservoirs of methane to have passed through that system, to have spilled off to the west. And certainly if you've got access to this type of tool when you're reconstructing basinal scale hydrocarbon systems, then you have an ability to understand the mass and migration of hydrocarbons through these types of systems. This is a short summary talking about gas water, volume ratios, open system versus closed system resolution. We can calculate the static geological estimates, show that a lot more water is involved than the static volume. That's because of the migration distance. And most importantly, it's consistent with an open system, and in that context, 8 reservoir volumes of gas have passed through this field. Now, I skipped over the carbon dioxide field. The noble gases can be applied to, I've shown you focus on hydrocarbons, but understanding carbon dioxide risk, carbon dioxide behavior is not just applicable to hydrocarbon exploration, but also the safe burial of carbon dioxide. We are developing still our understanding of how to use the noble gases to better date ancient fluids that are not just consistent with the ages you find with basinal fluid brines associated with hydrocarbons, but even older fluids. We found incredibly old fluids in the continental cratons. These, in fact, provide the source rocks for the helium resource that I was talking about earlier. And I will just leave you with this slide, just to, I hope, I've shown you some of the detail, some of the complexity of the data sets that we're dealing with. I hope, in some sense, how simple the interpretations are. But quantifying groundwater interaction at a variety of levels can have an impact on our understanding of the fluid flow, and we can use that as our baseline for water contact and the amount of flow through these systems. We can identify the origin of natural gases. We can identify where carbon dioxide comes from, whether it's magmatic or metamorphic, whether we're looking at trends across regions. We can identify the source of nitrogen. We can identify how to find commercial quantities of helium. And for the right circumstances, and it doesn't work everywhere, we can certainly place constraints on the age and the timing of the processes that we're looking at. And that is a good place to stop. Thank you very much.